Okay, so let's pick back up with the action potential here. If you just look at the brown part right here of the sarcolemma, does this look kind of like a capital T to you? Well, it did to the guys that were first looking at it. So they called it a T tubule. And you get this invagination, and the action potential goes down. And right on the other side, there are these big wells called terminal cisternae. These terminal cisternae have arms that go out called sarcoplasmic reticulum. So as the uh, action potential goes across them, the action potential flows across the sarcoplasmic reticulum. It would be like if I was getting electrocuted and you came up and grabbed me, what would happen to you? Well, you would get to ride the lightning too. So as the action potential goes down the T tubule and across the transverse cisternae, it also goes across the sarcoplasmic reticulum. That's going to cause the release of calcium. So that's going to cause the contraction. I'll come back to that in a second. But let's look at what we've got going on inside the cytoplasm here that's going to be affected by this calcium release. Remember, in the cytoplasm, we have the myofibrils. Don't get fibril mixed up with fiber. A fiber is a muscle cell. A fibril are proteins inside, and they come in two flavors, thick and thin. The thick myofibrils are called myosin. The thin myofibrils are actually several different proteins. The big two players are actin and troponin. And what troponin does is it sits down right on top of this active site of actin. It's called the active site because you see these little heads here on myosin, these look like little hooks. They want to bind to the active site, but they cannot because troponin is in the way. These little hooks are called the myosin heads, and they are pre-cocked. It's like having a gun uh, cocked and locked. I have a Colt 45, and you can carry it cocked and locked, and that means you've got a shell jacked into the chamber, but the safety's on. So you can carry it with one hand, one finger on the safety, and one finger on the trigger. And if you drop that safety and pull, you're ready to rock and roll because the gun is already has a shell in the chamber and it's already cocked. You don't have to do anything except drop the safety and you're good to go. Well, the troponin is acting like the safety here. As long as the troponin is in the way, myosin and actin cannot bind. You can also see that you've got this big, thick myosin head, and there's actin on either side, and there's also a gap. And these heads are going to pull this way, and these heads are going to pull this way, and that is going to make these two ends come together, and that's what's going to cause the contraction. Okay, well, what allows this? Well, the answer is calcium. When calcium is released from the sarcoplasmic reticulum, it pulls troponin off of the active site, pulls it to the side. See here, troponin is sitting right on top. Here it gets pulled to the side. When that happens, the myosin heads bind, and because they're already preloaded, boom, they contract, the muscle shortens in length. Now all you need is a way to uncontract them. And for that, we have to have ATP. ATP comes in and releases the actin and myosin link and recocks the head. And so now you either keep contracting or you don't, but that message comes all the way up from the brain. What happens if you don't have ATP? Well, I can actually give you a classic example of that. When you die, you quit producing ATP. Have you ever heard of rigor mortis? Rigor mortis is when dead bodies get stiff. The reason that they get stiff is because muscles are, always in some state of contraction, some muscles contracting. And without ATP, you cannot release the actin and myosin cross bridge, and so the muscle stays in whatever spot that it was in when you quit giving it ATP, and that's why you get rigor mortis. Okay, that's an awful lot of conceptualization from all of this. Like I said, it goes over about several pages, so I very much recommend that you read through it first and then watch this video and then go back and read through it again. And I do also recommend that you draw this out because I think it'll help you with vocabulary, and I think it will help you uh, get an idea of what goes where. and the flow of things. Okay, I will say this: probably of everything that we cover over AP1 for sure, this probably has the most one of the most challenging because it's got all this new vocabulary that you have to start with. Because if you don't know what a sarcolemma is, or a motor end plate, or acetylcholinesterase, you're dead in the water to begin with. But then once you have all of that down, then you've got to get the flow of events to what makes it all work. So one more time from the start. Message comes from your brain. It comes down to the second neuron, which is the motor neuron in the spinal cord, and it starts an action potential. This electrical impulse comes all the way down to the end, to the synaptic knob, where it releases acetylcholine, diffusing across the neuromuscular junction and binding to a receptor on the motor end plate of the sarcolemma of the muscle fiber. How about that? To prevent a sustained contraction, acetylcholinesterase is going to break up the acetylcholine within a few milliseconds. But from the moment that it binds, an action potential starts. It travels down the T-tubule across the transverse cisternae onto the sarcoplasmic reticulum where calcium is released. Calcium pulls troponin off of the active spot on actin, allowing myosin to bind to that active site and the myosin head, which is already precocked, to drop and cause contraction. ATP comes in and releases this bond and recocks the myosin head. And there it is.